Okay, some examples. Multivariate regression, two of which we've seen before. These are substantive examples, and I hope to walk through them in great detail relative to the measures in each one and interpret some regression results which aren't even here, to give you a flavor for what's going on here with respect to control. The control this time not introduced by random assignment, but by using multiple regression or multivariate regression. We saw this, I don't know where, I'm going to define everything here, so get a pen and get ready. This is the Michigan model of partisan voter choice, and probably used it in causal inference as an example. Let me walk through the pieces of it. So what we're saying is that partisan choice, at the end of the day, between a Barack Obama and a Mitt Romney, for example, is a function of at least three things at the same time. So one is party ID, partisanship. We've mentioned this. And it's the boss. So let's define it, talk about its scale. It's an ordinal scale, assume. The typical partisanship measure, we've already seen this, is a 7-point scale that runs from 0 to 7. Doesn't matter what the numbers are because it's only ordinal. -1, let's say, -2, -3, -2, -1, 0. +1, +2, +3, indicating on the negative side, not to cast aspersion on you Democrats, could score it the other way. The most extreme value on the left, -3, is the strongest Democrat, and the most extreme value on the right is the strongest Republican. So an ordinal scale here, I'm making this up as I go along. So here's what we're going to do on issues. We're going to first ask the voter what he or she believes to be the most important issue of the day. Then we're going to ask the voter to place both himself or herself on a scale and both of the candidates. And then we're going to do a simple calculation that illustrates how close the voter is to one of the two to each of the two candidates at the same time. And we'll call that an ordinal scale also. And here, I'm going to call this comparative candidate evaluation. I probably called it when we looked at it last time. I probably called it likability, the likability heuristic in a sense. You meet some people and you like them. You meet others and you don't so much. And I'm going to measure this in the following way, using a feeling thermometer. And forgive me if I've covered this in another video. If I have, we're just going to do it again, which can never hurt. So a feeling thermometer is a very popular survey research tool that produces at the end of the day something that looks like a ratio level measure. And the survey interviewer does something like this. She says, I want you to think of a thermometer that runs from 0 to 100, where 100 indicates maximum warmth and 0 indicates maximum coldness that you feel toward a person. And then typically a whole battery of people will be evaluated in that way. So there are people who, we're going to do Mitt Romney and Barack Obama on a feeling thermometer. And this variable is going to be the difference between those two. So if Mitt Romney is higher, then it's going to be a positive to go Romney minus Obama, and it's going to be negative otherwise. That's something like a ratio level scale, and a nice indication too of, in practice, how you sort of can wind up with variables that have attributes of ordinal and interval, ratio level, and so forth. This one I'm going to fudge even a little bit more because we're running regression models right now that require the dependent variable, y, to be measured at the ratio level. I made reference to that a couple of videos ago. Turns out we can do regression-oriented things with just the binary choice, Romney or Obama. But here's how we're going to measure that. We're first going to ask the survey respondents for whom they intend to vote, Romney or Obama. Then we're going to ask them how certain they are on a scale of 1 to 100. And do this vote intention here in something also resembling a ratio level measure where the certainty of voting for Obama, Romney minus the certainty of voting for the other candidate. So, say this is a ratio level measure then too. And then we have a multivariate regression equation. So you have a B1 and an X1, call X1 party IDs, and a B2, X2, call X2 the issue variable, and a B3, X3, call X3 the candidate evaluation variable. So you need a party ID, and we'll get to this in a minute, it causes both these things, and they can run the other way too. We're going to evaluate their joint explanatory value relative to the voting variable, the dependent variable y. And we do this now, once again, evaluate B1, B2, and B3 in terms of their meaning with the other variables in the model held constant, specifically. So look at B1, the effect of partisanship on vote. This thing is going to vary from 0 to 100, let's say, where 0 is certainty that you'll vote for Obama, and 100 is certainty that you'll vote for Romney, and all points in between constitute the variance, really. So I've got a 7-point scale here. B1 means as I move 1 point from, let's say, -3 to -2 in a positive direction, I realize B units on the y variable. So let's just say B happened to be 5. And this is a scale of vote choice, is a scale of from 0 to 100. If B1 is 5, then it means as I move 1 unit more Republican on the party ID scale, I realize a 5-unit change on average on the vote choice scale, holding the others constant. And the same is true for then you go to issues and so forth. Now every one of these things are going to have a standard error. Just as it was the case in the bivariate model. I'm not going to burden you with the formula that produces the standard error of the regression coefficients in the multivariate model, but alert you that, of course, that each one of them does have an estimated standard error, and each one will have an associated t-statistic, and it's exactly the same inferential game as it was in the bivariate model. You're looking for a t-statistic that's bigger than 2, more or less, and which would then produce a p-value, each one of them, less than 0.05. Typically, when you run these models at the presidential level with good data from a sound probability sample, all these variables will be statistically significant. And what that means is that that issues matter, even holding constant partisanship and likability. It means partisanship, of course, matters, holding these two constant. And lastly, it means that likability matters, holding those two constant. So you take like-situated partisans, that's what it means to hold something constant, say, hold it constant at -1, and like-situated people on the issues relative to the candidates, holding that constant. It still matters whether people like the candidate or not. So we're controlling here, and this is the idea in the observational context of doing causal inference and combining statistical inference is the notion here of control. Seeing if the relationship still holds when you hold constant other variables, in this case 2 of the other 3, when you hold those constant, do you still see a significant result? So you see t-values, super big t-value here no matter what for partisanship, really, really big too for issues and for comparative candidate evaluations, because all 3 of those dimensions come to play in determining voter choice in partisan in partisan elections. What we've tried to do here as best we can is to rule out the influence of a third variable. So if we only looked, for example, at a regression that involved vote choice and issues, and we saw a gigantic t-value, and we concluded then that that voters are issue-oriented, it would be a spurious result to an extent because partisanship wouldn't be controlled. In fact, if you run the bivariate regression of just voter choice on issues alone, just two variables, you'll see a spectacularly large t-value and a spectacularly small p-value that would in fact indicate that these two things were wildly, wildly related. When you add partisanship into the equation in a multivariate model, the t-value goes spiraling down for issues, and the p-value moves up for issues. Now, as I mentioned, all three of these variables will be significant, but by frequentist standards, they'll be statistically significant, but they won't be nearly as significant as each one individual in the multivariate context as they would have been had you just run three separate bivariate regressions. Example number 2. So we've been here too. Well, it's now been quite a while. So I'll remind you this illustration, the classic illustration of a spurious relationship between two variables. The setup here is dollar damage done by fires. So the unit of analysis here was individuals. The unit of analysis here is fires. So we have, what's that? N equals 1,000. If I recall correctly, I situated the problem in Philadelphia, Pennsylvania, and I don't know why. We're going to say we have data from 1,000 fires that took place in Philadelphia, Pennsylvania over a period of time, and we're going to score up across the 1,000 the amount of damage in dollar terms done by the fire, the number of fire trucks that responded to the fire and worked on it, and the size of the fire. And so, just in bivariate terms, we've now got here 2 x's. Let's say x1, here it is, fire trucks. x2 is the size of the fire. If I only look at this, y is a function of the number of fire trucks. I mean, it's this bizarre result where it appears as though fire trucks coming to the scene, the more of them that arrive, the worse the dollar damage is. So here you're an attorney now, and you see this plot, you go, I want to sue the manufacturer of the fire truck. They're causing damage and not limiting it. And that's a spurious result. What happens when you add in the multivariate model, when you add in a variable that represents the size of the fire, the sign on B1 will change. So you're holding constant. We're going to make this an ordinal variable. It's a 1 alarm, 2 alarm, 3 alarm, 4 alarm, 5 alarm fire. It's essentially the categorization of the size of the fire and the need to call for resources. And we should look at that original plot. It goes like this. Now I'm going to plot in space just the data from the 5 alarm fires. You've seen this already. And for a good measure, let's assume 200 are 5 alarm fires, 200 are 4 alarm fires, 200 are 3 alarm fires, and so forth. Well, for each of those categories, whereas we see this overall in the bivariate relationship between the number of fire trucks and the dollar damage, in each of the 5 categories, where we hold x2 constant, we'll see the real result. The real result is that will be that B1 will be negative. It in fact would be true that given similarly sized fires, bringing more equipment to the scene matters in a positive way. Brings down damage, which means a negative relationship. This actually works with real data. You flip the sign on the coefficient. You run this regression, we'll find one that you can do in class. Run this regression with just one x, and you get a statistically significant positive result. add in the control variable, and you get a statistically significant negative result. This will turn out B1 to be negative. This little story is a powerful recommendation of causal inference in an observational model where you don't have control. You certainly cannot, it would be immoral, to experimentally manipulate this problem so that you're sending a random half of fires everything that you've got, and a random half don't get the same treatment, serve as a control group. That would be immoral. So he's letting people's property burn. There are many things that can't be manipulated experimentally. We can't manipulate someone's partisanship. So the idea of the experimental manipulation of treatment and control doesn't work here. We have to do observational work. And even though there are plenty of well-informed critics of doing observational causal inference with a set of rules like this is a powerful story of control that doesn't come from random assignment. It does instead come from simply deploying a multiple regression model instead of examining bivariate relationships. So we're coming down then through these three. Third example, and then we're going to move on to dummy variables. Third example, contrived also. This is all true though. So I'm going to have an individual level unit of analysis as a person, and I'm going to contrive a ratio level measure of the probability that they will actually vote. So not a 0 or a 1, but something in the interval that relates to the probability that they will actually turn out. I might do this like this way. Find the number of elections, let's say, in the past 5 years in which they've been eligible to vote, and find the number in which they actually voted, and divide the second number by the first. So proportion that we're looking at the probability that someone's going to turn out and how it's related to age. This is not linear. Everything we've looked at thus far has been a linear relationship. As you move up 1 on x, you move up some constant value on y. Formula for the straight line. There are formulas for other lines, and sometimes formulae for other lines are what's appropriate to model a particular relationship, and this is one. Age and the probability of turnout, as it turns out, pun intended, they are very, very intimately related. From the day that you turn 18 to the day that you turn some number even north of my old person age, the probability that you're going to cast a ballot in a given election goes up. What happens is that young people immediately upon entering the electorate are at an immediate disadvantage because they are the most highly socially mobile group in the electorate. You move virtually every year, if not every year. And this affects the likelihood that you'll participate. The older you get, the more likely you are to settle down in one place and to know where it is you're supposed to vote every year and so forth. So this is going to go up, probability of voting on the y-axis, so y, and then age, just age, it's going to increase, and let's make the intercept here 18 because no one else going backwards matters. And so let's say it goes up, and goes up, and it continues to go up. And retired people over the age of 65, who've recently retired, this is the most dependable voting bloc among age cohorts in the United States. Older people go and vote. That's what they do. And then we become not so able to go and vote. And when we become, so you get out, I don't know what this age is, it goes up every year. But at age, sort of an average infirmity kicks in here. And people begin to not vote so much. And so what you have is not just a straight line, but a curve. That actually should be a familiar curve, not from 6th grade, but 7th. So someone taught you, all those years ago, they taught you the formula for a straight line. And you know we're using that as the basis here. I could rearrange that. But if any of you are scared, you need to rearrange it and show you that it's just the formula for a straight line for a bivariate regression model. This is a formula that you saw later on too. Challenge you to name it now. This is a restatement of the quadratic formula. And this is why you draw a parabola, again in a Cartesian plane. So you do a plot of x and y without the line in here, and you see data doing this, going up and coming down. That's diminishing returns. The line that you need to fit is not a straight line. The line that you need to fit is a polynomial, and you do that simply by adding x squared into a multiple regression model. That's all you do. Plop it in there, and the line will fit. The line will fit the data. In the event, there's nothing like this in political science, but in the event that your data went back up the other way, curved again, you just drop in the cube of x. Now x squared and x really highly correlated, but this too works. It works, and is a powerful illustration again of how useful the multiple regression model is as a tool to model data, to examine them from the standpoint of statistical inference. That is, all of these things will have associated with them a t-value and a p-value, to assess them from the standpoint of statistical significance, but also keep in mind that we're always in science interested in the causal story. And while these procedures are imperfect relative to the alternative, which is random assignment to treatment and control, they're not useless. They're very powerful in the hands of a skilled data analyst like yourself. The one thing I'll close with here is, again, the multiple regression model is not very well suited to examining one y and a dozen or 24 x's. A very prominent person in political methodology calls those garbage can models. You put everything in the garbage can, and when everything's in the garbage can, problems start to occur here. But for simple, well-conceptualized problems like these are very powerful. These are very powerful methods. Now, the next video is another sort of extension of regression using variables on the right-hand side, independent variables that are dummies, which is another word for dichotomous variables.